All right, let's go ahead and look through some of the necessary information to complete Lab 15. So this is one where we don't have a simulation. This was supposed to be a classroom activity where we'd each take our own birthdays or the current day of the on the calendar or something similar to that, and then run through and pretend it's going through different types of radioactive decay. But that's okay. We can still make this work. And to be consistent and make sure we're dealing with the same one, then as with the previous one of the other labs, we're going to deal with American Independence Day. So July 4th. July is the seventh month, and coincidentally, that just happens to be one of the easiest ones to ranges of numbers to use. So 7 doesn't have to be modified, it's just a 7. And then July 4th, again, looking at the ranges of numbers and the instructions here, then 4 is just outside of the range where we have to take any steps with it, so we're just going to use a 4. So the 7 is going to be the number of protons, and the 4 is going to be the number of neutrons. And we want to try to see what kind of a thing that would make. So from a periodic table, the 7 protons would tell us that we're dealing with nitrogen. And then because we've got 4 neutrons, then that's going to tell us that 7 plus 4 from these two going together is going to make 11 nucleons. So nucleons are things that live in the nucleus of an element. Putting this number together, we can name our full isotope. So if you've had chemistry before, but you've never learned about radioactive materials, you're probably familiar with the atomic symbol like this, where just N for nitrogen. But if you have like charges, like if you're dealing with ions and you get like a plus something or a minus something here, we're dealing with isotopes, then we're messing the stuff inside the nucleus instead of the electrons around the outside. So when we put this information together, then we would have nitrogen with 11 nucleons and then 7 protons. But because that's very, very difficult to try to type up and put in answer choices and on formula sheets, then a lot of times this is spelled out. So full name of the element, so nitrogen, and then 11 at the end is the isotope number. So it tells us the total number of nucleons, it tells us protons and neutrons combined, and it basically is like the radioactive flavor of our nitrogen. And so again, we would build this in class. We'd have a bunch of protons we'd put together. So 1, 2, 3, 4, 5, 6, 7, and then neutrons. There's 4 of those. So squeeze them in somewhere. 1, 2, 3, 4, and then we'd have a nucleus that would look something like that. If that's too much effort, then you could just list it out, 11 and 7. Pencil it 11 and 7, or you could just write again 7 protons, 4 neutrons. Okay, so now we want to make this initial isotope go through a couple of different kinds of decay and see what they look like. So if we're looking at alpha decay, then we need to remember that alpha decay is going to release what's called an alpha particle. An alpha particle is a helium-4 nucleus, specifically just the nucleus of it, or what one of these would be, because we're just shooting stuff out of the main nucleus and it makes its own nucleus when it leaves. So basically, a radioactive element will just start shooting things out, breaking down into something smaller in an attempt to be more stable. So helium-4, when we write in our notation, is usually this way. It's got 4 total nucleons, 2 of them are protons. So there we go. The total counters, particles, whatever pictures, if we were drawing, that would be leaving would be from 4, from the top number. And so we have a change of 4. The number of these that are specifically expelled protons, so conveniently we can see this without scrolling, but we still have that same helium-4, and the protons come from the bottom number. So that would be 2. And so if we think about what this makes, left over, right? So 4 total nucleons. I'm going to write it again just because we can't see it. The 4 total nucleons minus the ones that are protons, then that's going to give us 2 remaining neutrons. Okay, and then if we think about what we've got then, so I'm going to scroll down so I have a little more room to draw. We have our nitrogen 11. We're going to make it go through alpha decay, so sometimes there's a little alpha on the bottom of this, but we're just going to say that it becomes a helium-4 nucleus, or sorry, yeah, a helium-4 nucleus and something else called a daughter particle. So we want to know what's left over. We go through the numbers, top part together, bottom part together, and then just see what's left. So the original 11 nucleons that this would have had, 4 of them are going to leave, so there's 7 nucleons left, which unfortunately doesn't tell us what kind of stuff we're dealing with, because several different isotopes can have 7 nucleons, but different numbers of protons. Excuse me, and so they will be different elements in the end. Where we're going to get that information is from the proton numbers at the bottom. So nitrogen has 7 protons, minus the 2 they're going to leave with the helium is going to leave us 5. And it's that bottom number that we would need to look up. So that's going to be boron. If you think about what our picture looked like before, we had 7 protons, so proton, 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 and 4 neutrons, so neutron, 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 neutron. When the helium-4 leaves, basically it's just like this chunk of stuff just kind of going away. And if we look at what's left over then 1, 2, 3, 4. Oh, I didn't draw enough protons. There we go. 1, 2, 3, 4, 5 protons. So proton, 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 proton. And they're not really going to be distributed like this. Is just to have something to draw. And then the nucleus is going to have 2 remaining neutrons. So neutron, neutron. And then if we see, what's left over, we've got 5 protons, which we could have gotten from here, and 2 neutrons, which comes from just doing 7 minus 5 on these, or counting from the picture. But there we go. All right, so that's one example done. We're going to run through a couple more different types of radiation, see what these things turn into, and then go from there. Okay, so now we want to look at something called beta decay. And so we have beta plus or beta positive, different names for the same thing. And that's going to involve what's called a beta particle. So a beta particle is really strange, because a beta particle has 0 nucleons. So it's actually not a particle. It's technically a combination of particles, of smaller particles, and then it describes a certain type of change. So it's going to describe a transition. Either, depending on which version we have, a proton will transition into a neutron, or a neutron will transition into a proton. But if we look at this, the nucleons that leave, there's a 0 on top. So 0 nucleons leave. None. Just one kind of like swap sides. What happens is whatever number of protons we had, we're going to see the equation for it in a minute, but basically we seem like we lose a proton because of that bottom number. But notice that 0 actually fully leave, and what that means then is that a proton is going to switch into a neutron whenever we look at our drawing. And because these questions are just repeated to be, similar between the different types, so we can compare different forms of radioactive decay. Again, no neutrons are expelled. Technically, we even gain a neutron because we have a proton that transitions into a neutron. So our neutron count goes up, but technically we're not losing any counters or particles. I've got a bunch of red and yellow counters, like from grade school. Just bought a bunch from Amazon. And when we do this in the classroom, we just take one of those and like flip it upside down. It goes from red to yellow or yellow to red, depending on how you decide to set the colors. Okay, So if we want to look at our product and the thing that we were dealing with, we had boron 7, and then it's going to go through beta plus decay. So again, this is not really a beta particle, it's a combination of small particles, and then there's a transition inside the nucleus. But the math is easier to look at this way. 7 minus 0 is still 7. 5 minus 1 is 4, so it kind of looks like we lose a proton, but as it turns out, we don't. Okay, so that now, the 4 protons left over is going to be, from the periodic table, beryllium. And then if we draw through and we show this had 5 protons, so 1, 2, 3, 4, 5, and then 7 minus 5 means 2 neutrons, so neutron, neutron. And then what's going to happen in this transition is that a proton doesn't really leave or get ejected, but it just changes into a neutron and gets collected here. And so if we look at this then, we have 4 remaining protons and now 3 neutrons. Okay, so let's go back and see what the next one's going to be. So beta negative or beta minus decay, like before, is not technically a particle. We draw it out like it's one for the notation. But big clue here, it was beta plus before. We had a plus 1 on the bottom. Now it's beta minus, so you have a minus 1 on the bottom. But technically, because there's 0 nucleons on top of that, there's not actually any change in the total number of particles. We just have a transition again. Because of the way the equations work out, we would have something subtract negative 1 when we start looking at the protons on the bottom. So it looks like we gain a proton, which is going to mean that a neutron is going to transition into a proton. Which is going to line up to be similar with the next question. Because again, we're not expelling, losing, gain, like moving stuff in and out of the nucleus. It's just going to transition. So it's going to look like we're losing a neutron, but that's because a neutron is going to transition into a proton. All right, and then let's see if we can draw this out to get maybe a better understanding on it. In an equation form, so we've got our beryllium 7. So beryllium, the 7 total nucleons, 4 is the number of protons, which we can see on the periodic table. Then beta minus decay. So we have the symbol that helps us to run through this. 7 minus 0 means we still have 7 nucleons, so we didn't change our total number of particles. Then 4 minus negative 1. Remember, subtracting the negative 1 does a weird thing, but it becomes like adding 1, and this becomes 5. So 5 protons is something we've seen before. That's boron. So, if we look out the inside of what the nucleus would be, or if we put counters on the table or you could use quarters or coins or something even if you wanted to try this at home. But we would start with 4 protons. So 1, 2, 3, 4. And the arrangement's really not important here. So the protons come from the bottom number. Total nucleons is 7, so I need to add neutrons until we get to 7, or you can subtract and then see what the difference is. But I'm going to have 3 neutrons, so neutron, neutron, neutron. And then subtract negative 1. Again, it looks like we're adding a proton, and that's because from our answers earlier that a neutron is going to transition into a proton. So a neutron here is just going to turn into a proton. And then we start to go back and count all of these up. Opposite process from what we saw in question 12. But now we're going to have 1, 2, 3, 4, 5 protons. And only 1, 2 neutrons. For a total of 7 nucleons. All right, and then last page from the paper assignment. So gamma decay is the only one that doesn't actually evolve any particles at all. Gamma decay is just a release of pure energy in the shape of a photon. And it's not even like a visible photon. So you might think photon, hey, that's light, we can see that. But gamma rays are such high energy that when it releases, it's not going to be a thing you can see. It's even beyond X-ray for the most part, usually. Um, so we don't really have a notation for this. Normally, we just kind of throw gamma down and gamma 1, gamma 2, if there's multiple different gamma waves, gamma rays that are released. If we wanted to put a notation to it to make the equation work out better, then technically we'd have 0 protons, 0 particles, 0 anything. And so that would lead to 0. So then if we're not even changing, we're not losing, we're not altering, nothing's going to happen to the particles in the nucleus. So again, we could say 0, 0 means that there's 0, there's nothing. I forgot to put my, there we go, just to be consistent with how I wrote the other zeros. So one more time, how many encounters or particles would be expelled? Well, none, because again, gamma is just gamma rays, and even the zeros are not usually on there, but I'm just doing that as a reference. It means that nothing is leaving except pure energy. And if we try to write that out as an equation, again, this is very, very strange. Then we'd have some kind of like excited state boron, and normally show that with a little star asterisk to show that it's got extra energy. Then that's going to release a gamma ray. If it were multiple, we'd have gamma 1, gamma 2, gamma 3, so on if there were more. And then it just drops back down. Oops. To boron like it was before. So the picture itself wouldn't change at all. We'd have 5 protons like we had for the other, for any boron really, 2 neutrons for this specific flavor. It's got energy, so woo, energy. I guess I don't know what else to do with that. And then that's going to release as a gamma ray, and then what's going to turn into is now just a normal boron, no extra energy. So from this, we'd have 5 protons and 2 neutrons. And comparing to the other questions from earlier, we've already seen boron in this format. And it's the same as before, right? This boron 7,5. So question 16, yeah, see, look, boron with the 7,5. And then where else did we have that? Question 8. Yeah, question 8. So all of these have been the same. The final product on those have all been identical. So as far as the extra part on the question, it's the same ultimate picture at the end. And that's it.